Hey there, science fans. Welcome back to another exciting episode where we unravel the mysteries of the digital world. Today, we're diving into the fascinating world of computer networks, specifically routing. Routing is like the unsung hero of the internet, making sure everything runs smoothly behind the scenes. Imagine you're sending a postcard. You carefully write down the address, stick a stamp on it, and drop it into the mailbox. You wouldn't just throw it into the wind and hope for the best, right? That would be chaotic and unreliable. You need the address and the postal service to get it to the right place. The postal service ensures that your postcard travels through a series of well-defined steps to reach its destination. Routing on the internet works similarly. It's the process of selecting the best paths for data packets to travel across networks and reach their destinations. Just like the postal service, routers and switches in a network determine the most efficient path for data packets to travel. They consider factors like network congestion, the shortest path, and the reliability of the route. Without routing, our online world would be a chaotic mess. Data packets would collide, get lost, or take forever to reach their destination. No emails, no cat videos, no online gaming. Not cool. Imagine trying to stream your favorite show and it keeps buffering endlessly. Just like a well-organized postal system, routing ensures that data packets arrive at the correct destination quickly and efficiently. It optimizes the flow of information, making sure everything gets to where it needs to be without unnecessary delays. It's the invisible force that keeps the internet humming along. Every time you send an email, stream a video, or play an online game, routing is hard at work behind the scenes. So next time you're browsing the web, take a moment to appreciate the magic of routing. It's the backbone of our digital lives, ensuring that we stay connected and informed in this fast-paced world. Now, there are two main ways we route data, statically and dynamically. These methods are fundamental to how our networks operate, each with its own set of advantages and challenges. Static routing is like having a predefined route for your mail. Imagine a mailman who follows the same path every day, delivering letters and packages to the same addresses in a fixed order. It's simple to set up, but not very flexible. This method works well when the network environment is stable and predictable, with little variation in traffic patterns. Imagine if your mailman could only use one route, even if there was a traffic jam. This lack of flexibility can lead to inefficiencies and delays, especially if unexpected issues arise on the predetermined path. Dynamic routing, on the other hand, is more adaptable. It's like having a smart navigation system that can adjust the route based on current traffic conditions. It's like having a GPS for your data packets. This system can reroute data in real time, avoiding congested paths and finding the quickest way to the destination. Routers using dynamic routing talk to each other, sharing information about network conditions. They constantly update each other on the status of different paths, ensuring that data can be sent through the most efficient route available. They can then choose the best path based on real-time traffic. This adaptability makes dynamic routing particularly useful in environments where network conditions can change rapidly. Static routing is often used in smaller networks with predictable traffic patterns, for example, in a small office or home network, where the number of devices and the volume of data traffic are relatively low and consistent. Think of a small office or home network. In these scenarios, the simplicity and reliability of static routing can be a significant advantage. Dynamic routing shines in larger, more complex networks like the internet. These networks have a vast number of devices and highly variable traffic patterns, requiring a more sophisticated approach to manage data flow efficiently. It allows for more efficient use of network resources and faster data delivery. By continuously optimizing the routes, dynamic routing ensures that data packets reach their destination as quickly and reliably as possible, even in the face of network congestion or failures. Network engineers often use a combination of both static and dynamic routing to balance simplicity and flexibility. This hybrid approach can provide the best of both worlds, ensuring stable performance while also adapting to changing conditions. As our networks continue to grow and evolve, the importance of choosing the right routing method becomes even more critical. Whether it's the straightforward reliability of static routing or the adaptive efficiency of dynamic routing, understanding these approaches helps us build better, more resilient networks. Routing protocols are the languages that routers use to talk to each other. They help routers discover networks, exchange information, and make decisions about the best paths for data. Think of them as the rule books for routing. Three common routing protocols are RIP, OSPF, and BGP. Each has strengths and weaknesses, making them suitable for different network environments. RIP is like the old-timer who prefers simplicity. OSPF is the meticulous planner who wants to know every detail, and BGP is the global diplomat connecting networks across the world. RIP, or Routing Information Protocol, is like counting the number of intersections on a map. Imagine you're navigating through a city, and each intersection you pass through is a hop. The fewer intersections you encounter, the quicker you reach your destination. This is essentially how RIP functions in a network. It determines the best path based on the fewest hops or routers between the source and destination. Think of it as choosing the shortest route on a road trip. The protocol counts each router as a hop and selects the path with the least number of hops, ensuring data travels efficiently from point A to point B. RIP is simple to configure and works well in smaller networks. For instance, in a small office setup where the number of devices and routers is limited, RIP can be an effective and straightforward solution. Its simplicity makes it a popular choice for those who need a quick and easy way to manage network routing. However, RIP has its limitations. While it's easy to set up, it's not without its drawbacks. One major issue is its inability to scale effectively. It has a maximum hop count of 15, meaning it can't handle large networks. In larger, more complex networks, the number of hops can easily exceed this limit, making RIP unsuitable for such environments. This restriction can lead to inefficiencies and potential data routing issues. It also doesn't consider network congestion or other factors that could impact performance. Unlike more advanced protocols, RIP doesn't take into account the current state of the network, such as traffic load or bandwidth availability, which can lead to suboptimal routing decisions. RIP is like taking the scenic route, even if it means encountering some roadblocks along the way. While it might get you to your destination, it may not always be the fastest or most efficient path. In summary, while RIP is a simple and easy-to-use protocol for small networks, its limitations make it less ideal for larger, more dynamic environments. Section 5, OSPF, Mapping the Network for Efficiency. OSPF, or Open Shortest Path First, is like having a detailed map of the entire network. It creates a complete picture of the network topology, including all routers and links. This allows OSPF to calculate the shortest paths based on factors like bandwidth and delay. OSPF is more complex to configure than RIP, but offers better scalability and performance. It's well suited for larger networks with complex topologies. OSPF is like taking the expressway, bypassing the traffic, and getting you to your destination faster. Section 6, BGP. Connecting the world of networks. BGP, or Border Gateway Protocol, is the protocol that makes the internet possible. It's responsible for routing traffic between different autonomous systems, which are like countries in the world of networks. BGP is a policy-based protocol, meaning network administrators can define rules for how traffic is routed. This allows for greater control and flexibility in managing internet traffic. BGP is like the United Nations of routing, ensuring that networks can communicate and cooperate on a global scale. Section 7, Comparing Routing Protocols. A quick look. Let's summarize the key differences between RIP, OSPF, and BGP. Feature RIP, OSPF, BGPE. Metric hop count, cost as path. Policies scalability low. High, very high complexity, low, medium. High use cases. Small networks, simple routing, large networks, efficient routing, internet routing, inter-AS routing. Section 8. Real-world routing examples in action. Imagine a small office network with a few dozen computers. RIP would be a suitable routing protocol in this scenario, as it's easy to configure and manage. Now picture a large university campus network with thousands of devices. OSPF would be a better choice due to its scalability and ability to handle complex network topologies. Finally, consider the internet as a whole, with countless interconnected networks. BGP is the glue that holds it all together, enabling seamless communication between different parts of the world. Section 9. Conclusion. Keeping the data flowing. Routing is the unsung hero of the internet, ensuring that data packets reach their destinations quickly and reliably. Whether it's the simplicity of RIP, the efficiency of OSPF, or the global reach of BGP, each routing protocol plays a crucial role in keeping the world connected. So next time you're online, remember the amazing world of routing happening behind the scenes. And that's routing in a nutshell. Keep those data packets flowing and stay curious, science fans.